Sorry for a slight delay. Let's get started. So last Wednesday, we started putting together a model that is going to end up in a linear system that we need to solve. And the great this is one of the great examples and one of the standard examples of how we arrive at solving a linear system while trying to solve a differential equation numerically. So no matter the differential equation, sooner or later, you're going to arrive at solving a linear system. Different methods and different equations will have a slightly different process at getting that linear system. But solving linear systems is at the core of numerically solving differential equations. And numerically solving differential equations is pretty much fundamental to science and engineering. Okay? So this is why the topic of linear systems is actually really important. So what did we go through last time? We have a model of a heated rod. Here's my rod, or my rendering of it. The wall on this side is heated at 40 Celsius degrees, and the other wall is heated at 200 degrees. I have ambient air at 200 degrees, 20 degrees Celsius, and the rod is not insulated, so I'm losing some energy / temperature to this, to the ambient, to the air. So I'm interested in what is the temperature. If I'm keeping this at 40 degrees and 200 degrees, those are my boundary conditions, what is the temperature of this rod? Now there's a differential equation that actually solves this, that basically says that the second derivative of the temperature distribution, this is modeled as one-dimensional system, so temperature is basically function of x along this direction, plus h, which is the heat transfer between the rod material and air, and times the difference. Of course, the larger the difference, the more transfer overall I will have. Okay? So if this is at 0 Celsius degrees, of course, this rod will cool faster, right? Because it will lose more energy. So basically, that has to be equal to 0, and that differential equation is valid everywhere in this rod. How to arrive at an equation like this from heat transfer principles, you will learn in transport phenomena class. But now we will just actually take that differential equation. In your differential equation class, you've learned how to solve this analytically. I don't care if you know how. I'm not going to ask you to solve this analytically here in this class. I just assume that you know how to do that. We will focus at arriving at numerical solution. Now, numerical solution, okay, the principles are as follows. We cannot solve this everywhere. We cannot look for a function t of x that solves this. Not a single function. That's the business of solving it analytically. What numerical solutions do, they're looking for solutions at specific points. So I go and discretize my world into number of points, and I'm looking for solutions at those points. So here, I'm naming those points x1, x2, x3, x4 along x direction, and temperatures at those points are T1, T2, T3, T4. Now, this is still part of the same, this differential equation that I put up there is still valid at those points. But I need to, in addition to discretizing my space, so by identifying this x1, x2, x3, x4, I have discretized my space. I also need to discretize the equation itself. Okay? I need to figure out what are some sort of simplifications for these differential operators. And we go to finite differences for that. We already know that the slope of this function t, I can approximate actually in 3 different ways at neighboring points. So if I have, where's my mouse? All right. There we go. If I have point x, then the derivative of t at point x, so this is at x, can be approximated as t of x plus delta x minus t of x minus delta x divided by the difference between the 2 points, which is 2 delta x, right? I can do that also. This is called a central difference because I'm looking at the points around me and I'm in the center, right? X is in the center, t of x plus delta x is on one side, t of x minus delta x is on the other side. I could also have a so-called forward difference. So basically, I'm just looking at t of x plus delta x minus t of x itself divided by delta x, or the backward difference t of x minus delta x divided by x. So these are all approximations to the derivative. They're called so-called finite differences. I can also now recognize that my second derivative is actually derivative of dt dx, derivative of a derivative, and I can apply this to a derivative, and if you actually did so, you would get that this is, and use the central differences in both cases, you would actually get that this is an approximation for second order derivative. So we're just gonna use it. Okay? So this is our starting point. So now we actually need to basically apply this operator at point t1, at this point. Okay? So for this point t1, my t of x plus delta x is difference between these 2 points, is going to be basically t of x2, right? So t of x2 minus 2t of x1 and plus t of x0 divided by delta x squared is the approximation for the second order derivative at this point 1. Do we agree? Okay, so let's write that down. So basically now we discretize differential equation, ODE, ordinary differential equation, at point x is equal to x1. So basically t of x1 is t1, right? So if I do that, basically I will have, let me show the equation as well. So basically my t of x1 plus delta x is essentially t of x2 minus 2t of x1, so I'm following this differential operator, plus t of x0 divided by delta x squared. So this is my the second derivative of t discretized at x is equal to x1. Yes? Everybody sees that?
What is ODE?
Ordinary differential equation. Very common acronym. ODE, PDE is partial differential equation. So basically that operator is discretized like this. So this is an approximation. And I'm applying it at this point, t of x1. And then I have plus h of t air minus t, which is at this point, t of x1, is equal to 0. For some reason, I chose to write in blue. Is everybody okay with that? No? You want me to change to?
Green.
Green?
It's okay.
Oh, no, green will be screaming at us. Green I will veto. This green is not good. How about black?
What about white?
You really want to cancel this class, don't you? All right, so what is t of x2?
No, I'm already.
T2 minus 2t1 plus t0. Oh, really?
It's a sign.
Sure.
Go home to your babies.
My babies are having fun in daycare. They'd be like, why are you here?
Do they look forward to going to daycare?
Yes, they do. They really do.
My little girl, she's like, wanna go to Christy's house? Wanna get back to Christy's house and see friends?
Okay. 9953. This system. It's giving me the same trouble as on Monday.
So you have to completely restart it, refresh the screen and everything?
It doesn't want to update this code. And I'm entering, and it still doesn't. And when I enter it here, it says incorrect code was entered. Let's try VGA. And VGA has also traditionally given me issues after VGA. Yeah, it's the same stuff as on Monday. Like it just freezes the code and it should update it because every time that there's a disconnection, there's a new code. And for some reason it doesn't. But when I enter what I see here on the screen, 9953, it tells me that's not the correct code. Because I know that it should change it, so it's some sort of security issue, I'm guessing. 9953. Confirm incorrect code was entered. And VGA doesn't want to do laptop VGA. I'm gonna continue the class and call IT because it was fine on Wednesday. I never did screen up, power off. Well then, you're writing on the board again.